So welcome back again. We were discussing about the how our quartzite can be converted into a polysilicon rod. So we have already done this discussion in the last lecture, and in that lecture we have already seen that how quartzite and different processing can be done to convert the quartzite into MGS, metallurgical grade silicon, and thereafter it can be further processed to get the electronic grade silicon, which is polysilicon. And we are saying that the polysilicon, which is means after converting the MGS into EGS, it will be a very ultra pure electronic grade silicon. Okay, it will be very ultra pure, and we can say that it is almost 99.9999% pure. That can be identified by seeing these numbers. Okay, we can calculate the number of impurities in per centimeter cube volumes of this particular crystal. So within this volume, the number of impurities will be this much, but at the same time, the number of silicon atoms will be this much. So you can calculate the purity of this particular polysilicon that we got. So now we have to look at, as I have already told you, after the getting the polysilicon. So polysilicon, which is our EGS will be the raw material for drawing the single silicon crystal. Okay. So now we have to look at how this single silicon crystal will be drawn off from this polysilicon. Fine. So this is our today's topic. So let's start with that. So as I told you that for drawing the single silicon crystal, okay, if we want to draw the single silicon crystal, there are two different mechanisms that we have. Okay. So either we can go for the Czochralski process, or we can also go for the float zone method. Okay. So there are two ways. In your syllabus, we have mentioned for the Czochralski process. Okay. So we have to go through the process, which is actually developed by the Czochralski, one of the scientists. Okay. So that we have to look at. In the last lecture, I also explained you that the polysilicon rod. Okay. So I told you about this picture, if you remember, that the polysilicon rod that we have got. Okay. Sorry, the polysilicon rod, this is the polysilicon rod that we have got. Okay, so this either can directly be used if we are using the float zone method. Otherwise we have to crush them into pieces if we are using the Czochralski process. Okay, so we have to deal with the Czochralski process. So that's why this rod will be crushed into the pieces, small pieces, and this will be called as the charge. Okay, it will be called as the charge. So now just try to look at the process. Okay, what is this process? So first of all, in Czochralski technique, okay, in the Czochralski technique, it was invented in 1918. Okay, and this is the basic system. Okay, I have taken this picture from the SMG book. Okay, so you will find this picture there. And this method is also called as the liquid solid mono-component growth system. Okay, remember this, another name of Czochralski technique is liquid solid mono-component growth system. So now we have to look at one by one what are the different components of this particular system. So it may look very complex system. So we have to look at what are the different systems that we have. So basically in this system, first of all, we have a particular crucible. Okay, you can see in this particular picture, we have a particular crucible. Okay, so this crucible is nothing but a cup. Okay, you can say that it is a cup, or like the place where we have to place our charge. Charge means the crushed polysilicon. Okay, so this particular cup, or you can say the crucible, okay, this crucible is made up of quartzite. So quartzite is also called as quartz, okay, right? So in the short form, you can call it as a quartz. So quartz is nothing but your SiO2. Fine. So one thing that we need to remember is that uh, because we want to grow a very high purity single silicon crystal, okay, so what we need to take care of, that there should be no impurity incorporated while growing the single crystal. Okay, so we have to choose such material, okay, that should be made up of silicon only. Okay, if it is some other material, then in this process, because in this process what we have to do, I will tell you one by one. But one thing I want to tell you now is that we have to heat the charge, as I have already explained, charge is the crushed silicon polysilicon rod. Okay, so when we crushed into the small pieces, you will find that this type of pieces will be there. Okay, and I will be calling this as a charge. Fine, so it is placed inside the silica crucible. Okay, so you just see this is our silica crucible. So within this we have to place the charge. So this is your polysilicon. Okay, so it is broken up into small pieces. So now we need to heat them up. Okay, we have to heat them up so that it will get molted. Okay, so it will be converted into a liquid state. Okay, so it will be converted into liquid state. So that's why if we choose this material of a different element, and that time different element or some other compound, then there is a chances that that may also melt it down. It will mix with the molten silicon. Okay, and therefore it will make it impure. Fine, it will make impure. So that's why we need to choose this silica, means crucible made up of silica, okay, which is your quartz. So you remember that still the quartz is considering oxygen, because silica means your SiO2. Okay, so this crucible is made up of SiO2, and there is a chances that when we heat this particular charge, okay, this charge, if we heat up to its melting point, then there is a chances that this crucible will also melt a little, and then this oxygen will enter into this particular melt. Okay, and it will be available. Fine, it will be available with the silicon, and it will be make it contaminate. Okay, so it will contaminate this particular molten silicon. So that we have to remember. One more thing that we have to remember is when this process of single silicon crystal growth is over, okay, this entire system will be cooled down again, and that time the silica crucible will cracks. Okay, it will crack down. Okay, it will cracks, and it cannot be reusable. That you have to keep in mind. It cannot be reusable. Okay, it will be cracked. Okay, so when it will crack, it cannot be reusable. Okay, so we heat up, and then again it will cool down. So when it will be cooled down, then it will be cracked. Okay, and it cannot be reused. So now after this crucible will be placed over a graphite crucible. You can say it is the outer jacket of the crucible. Okay, so we have the inner jacket is made up of silica, and the outer jacket is made up of graphite. Okay, so this is the outer layer of your crucible. Okay, so that cup is actually surrounded by this particular graphite jacket. Now this graphite jacket will be placed over a graphite heater. Okay, this is our heater, so a graphite heater will be there. Fine, so this graphite heater will be provided for heating this particular charge placed inside the crucible, and that will be done by RF induction heating. Okay, radio frequency induction heating. So actually this heating can be done either by the radio frequency heating, or it can be a resistance thermal heating. Okay, both can be used. Fine, but most of the time we are using your RF induction heating. Fine, so whenever there is a very large charges, at that time we can go for the resistance thermal heating. Otherwise, this will be used prominently. Now, after this, you can see we have the graphite heater. Then again, we have a thermal shield. Fine. So that this thermal shield will confine the temperature within this area. Okay. Within this area, it will confine the temperature. Right. Then after this, again, we have a big chamber. Okay. You can see that the entire system is actually placed inside a big chamber. Okay. This big chamber is again made up of quartzite. Fine. This big chamber, you can see this big chamber is again made up of quartzite. Okay. So after all, we have to keep the environment as a silica. Okay. So if anything goes wrong, then again, if something get mixed with this particular molten silicon, then it should be silicon only. It should not be other thing. If other thing is getting mixed up, then it will contaminate it. Fine. So now what we have to have is this chamber, okay, which is made up of silica. So initially we have to evacuate it. Okay, there should be no other gases present in this particular environment. Okay, it should be evacuated first, so that the other gases present in the atmosphere should not be there. Okay, so we have to evacuate so that all other gases will be removed. And after that, because for this particular processing, okay, whatever process we are going to follow for growth of the single silicon crystal, we need to maintain a certain atmospheric pressure. Okay, so to maintain that pressure, we need to insert a certain gas. Okay, but we have to keep in mind that gas should be an inert gas. Okay, it should be an inert gas. If it is not an inert gas, then it will be making a reaction. When the entire system will be heated, it will make a reaction, it will make a particular product. Fine. So what we need to do is we have to insert an inert gas. So in this case, what we are using the argon gas. Fine. So we are using the argon gas, and then this argon gas will be allowed to enter to the system within this particular outer jacket. In the complete system, it will enter, and then it will maintain the requisite pressure. Okay. So first what we did, we have evacuated the entire gases present in the atmosphere. Okay. Then we have let the argon in to maintain the requisite pressure. Now you can see in this system what other components that we have is, you can see generally we have to cool down this entire system. Okay, so the things are not actually shown over here, but this entire system may have a water cooling mechanism. Okay, that may be placed outside this. Okay, so there will be a water cooling mechanism so that its outer jacketing, okay, this must be kept at low temperature. That is because the molten temperature for your silicon is about 1412 degrees centigrade. Okay, so when we heat it up to that much of temperature, there obviously the other parts will also get heated. Okay, so to maintain it to low temperature, we need to cool down the entire system, and that's why we need a cooling mechanism. So that can be a water cooling mechanism that may be connected over here. Then you can see we are having a different viewing points just to see whether it is growing properly or not, and everything is correct inside the chamber. Okay, then you can see we are having a different other components. So that components we have to look at. So you can see first of all this entire crucible which is placed on a graphite jacket. Okay, this particular system is placed over a shaft. Okay, there is one crucible shaft. Okay, you can see here we have a crucible shaft. So it is placed over a crucible shaft. Okay, and you can see there is a rotation of this shaft. Okay, so this rotation, you can see it is clockwise rotation. You can observe that it is rotating clockwise. Fine. So it means that the entire cup, or the entire crucible, it will be keep on rotating clockwise direction. Okay, it will be keep on rotating like this. Okay, it will keep on rotating. So it is not like stably present. It is keep on rotating. It is making a clockwise rotation through this shaft. Fine. Now you can see we have another mechanism, other part of the system. So other part of the system is you can see we are having a pooling mechanism system. Okay, we have the crystal pooler, so we have the pooling mechanism system. It's connected over here. Fine. So this is again a pooling shaft we have. Okay, you can see here it is written as a seed shaft. Okay, so this shaft is having a holder connected at this point. Okay, so this is called as the seed holder. Okay, so you need to understand how this crystal growth will take place. Okay, so one shaft is there, and from this shaft one seed holder is connected. Okay, so what is the function of the seed holder? This seed holder will hold the seed. Okay, so it will hold a crystal seed. Fine. So that crystal seed will be placed at this particular point, right? And this particular crystal, single our crystal silicon seed will have a particular orientation. Okay, so we need to place a crystal of silicon, which is we are calling as a seed, okay, of particular orientation. Okay, I will tell you this orientation is very important. So I will do the discussion over the orientation of any crystal. Okay, if we have a silicon crystal, then what we mean to say the orientation that we need to describe, because it is very important thing. Okay, so first of all, now we try to understand this. We are having particular crystal uh, pulling shaft, okay, pulling mechanism, and through this pulling mechanism, we are having a seed holder, and to this seed holder, one of the crystal of silicon, which is we are calling as the seed. A seed crystal will be connected to the seed holder, and it is having a particular orientation. Okay, a particular orientation of the crystal planes. Okay, so that particular orientation we have connected over here. Okay, so now what happens is, so how it works, that we have to look at. Okay, if you understood the various component, various part of this particular system, then you can now try to understand the working mechanism. Okay, how it works. So basically we are having this sheet shaft or puller shaft, you can say. So you can see our crucible shaft is actually rotating clockwise, and it is having a anti-clockwise rotation. Okay, so it is rotating anti-clockwise and it is rotating clockwise. Okay, so it is counterclockwise rotation, it is clockwise rotation. Now we need to understand what is the use of this rotations. Fine, and how it will be done. So first of all, what we need to do, first we need to place the charge, our polysilicon, crushed polysilicon, into the crucible. Then it must be evacuated first. This entire chamber must be evacuated first, then the argon gas will be placed. Okay, so we allow the argon gas to maintain the requisite pressure, and then RF heating will be done. So RF heating will be done, and its temperature will be raised up to 1412 degrees centigrade, which is the melting point for your silicon. So your silicon will start melted, and then it will be converted into this. This was solid earlier, and now it will be converted to a liquid phase. Fine. And now what we can see is, I just told you that this particular cooler system, okay, pooling mechanism system, this system will be holding this seed crystal in the solid state. Okay, so we are having a seed crystal of silicon of particular crystal plane. Okay, that will be connected And now when this is already in the molten state, this shaft will be lower down. Okay, it will be brought down, and uh, it will be pulled down so that this seed crystal will be start touching the surface of the molten silicon. Okay, so it will start touching the molten silicon surface, and then when this seed crystal starts melting, then there will be a mechanism that will start pulling up this particular seed crystal. Okay, so remember this operation, how it is done. Okay, how this single silicon crystal will be growing. So first of all, this will be this is a silicon will be melted down. Okay, after raising the temperature, and while then the seed crystal will be can be kept here in the air. Okay, it will be not touching the surface. So once it is converted into the liquid phase, okay, it is get molten, then we can slowly lower this particular seed crystal, and now the seed crystal, when it starts touching the surface, okay, we have to lower it as much when it will be starting just touching this particular surface of the molten silicon. When this seed crystal starts melting, okay, slowly, then this shaft will start pulling up the seed crystal. Okay, so what we can understand, the temperature at this point will be much larger than the temperature just above the surface. Okay, so that we can understand, because we are heating this particular silicon which is available in the crucible. Fine. So obviously the temperature of this particular molten silicon will be much higher than anything which is placed in the air at this point. Okay, so what we need to do is, as soon as your seed crystal starts melting, then we have to pull it up. Okay, and when we pull it up slowly, okay, there is a means particular pulling rate that we have to choose. Okay, we cannot pull it too fast, we cannot pull it too slowly. Okay, there must be a certain pulling rate that we need to maintain. Okay, if we are able to maintain the certain pulling rate, then only a particular diameter of the single silicon crystal will be formed, otherwise it will not form. Okay, so that we have to take care. So cooling rate will be deciding what diameter of the single silicon crystal will grow. Fine. So a particular pulling rate should be maintained. So as soon as we start pulling up the seed crystal, you know that this particular molten silicon will stick to the surface of your seed crystal. Okay, so when it is already stick to the surface of the seed crystal, when we pull it up, then this will start its temperature will starts getting down. Okay, and when the temperature starts getting down, it will be starts solidifying. Okay, so we have to maintain the cooling rate such that, okay, so typical cooling rate, I will tell you, it is some few per minute, I hope. So that is the typical cooling rate you will get. Okay, so we have to maintain the cooling rate such that, so as soon as we start cooling it slowly, then its temperature will cool down and it will be automatically start solidifying. Okay, now the thing is that whatever the template that we have taken, template, and I mean to say that the seed crystal orientation. Okay, whatever the seed crystal we have taken, the silicon seed crystal we have taken, whatever be the orientation of its surface. Okay, okay, so I will tell you about the orientation. Okay, what we mean to say the orientation of the crystal. Okay, it is very important point. Okay, so whatever be the seed crystal orientation, so generally we are taking 1 1 1 1 plane. Okay, 1 1 1 plane. Okay, generally we are taking 1 1 1 plane. So why we are taking 1 1 1 plane, that I will also explain you later. Fine. So generally, whatever be the orientation of the seed crystal, whatever the crystal is growing or solidifying, it will also take the same orientation. Okay. So this way, it will, the entire crystal that we are growing, it will be having the same crystal orientation. Okay. It will not have a different crystal orientation. Okay. And this way we can get a single silicon crystal, okay, that will be pulled up slowly, and it will take a lot of time to do. Okay. And then a particular diameter can be obtained. So how the diameter can be obtained, a particular diameter, by controlling the pooling rate. So from this discussion, I hope you must be able to understand in this system, okay, this pooling has to be done with a very specific rate to obtain the like particular diameter of the single silicon crystal. Okay, so obviously it cannot be done manually. Okay, this polling cannot be done manually. So this system is actually a computer controlled system. Okay, it will be an automatic control system. Okay, there will be a program. That program will be controlling everything. Okay, it will be keep observing the temperature of this, and then they will be lowering down this particular seed crystal, and then it will be observing as soon as it starts melting down, it will be pulling it up with a particular rate. So it will be automatically controlled by a microprocessor control system. Okay, so that we have to take care. Now, so I think the operation must be clear from this discussion. Okay, so this way we are growing the single silicon crystal. So you can see the basic points that I have told you. Basically, this entire system is divided into three different parts. Okay, so basically the components of the crystal puller. Okay, you can see. So this entire system is also called as the crystal puller. Okay, simply a crystal puller. Okay, so this is containing the basic components are a furnace. Okay, a furnace which includes the fused silica SiO2 crucible, a graphite susceptor, a rotation mechanism, a heating element, and a power supply. Okay. Then a crystal pulling mechanism which includes a seed holder, a rotation mechanism system. Okay. An ambient control which includes gas sources like argon, and flow control and an exhaust system. Okay. So basically, I told you everything about this, but one more point that I forget to tell. I told you that this is rotating counterclockwise and this is rotating clockwise. So what is the use of this rotation is, actually this is keep rotating to maintain the temperature within this crucible uniformly. Okay, so there should be no local heating. It should be not like that you at one point the temperature is higher, at the other point the temperature is lower. Okay, so what is the use of keep it rotating? It is rotating clockwise, it is rotating counterclockwise to maintain the uniform temperature throughout this crucible, so that the entire crucible will have the, or this particular molten silicon should have the same temperature everywhere within the crucible. So this is the use of it. Now one thing I told you that when we are molting it, okay, when we are hitting this charge, then obviously this charge will melt down, and obviously this silica crucible will also start melting down. Okay, it will also melt down, and obviously it will incorporate the oxygen. Okay, as an impurity it will incorporate the oxygen, that we have to see later on. So obviously it will be incorporating the oxygen. So this is one of the disadvantage. Fine, one of the disadvantage. And I let you know that it is not always be a disadvantage, sometimes it is also advantageous. Okay, sometimes it is also advantageous because it is giving the mechanical strength to your silicon. Fine, so it is disadvantage as well as it is advantageous in some moments. Then you can also see we are having the graphite crucibles. Okay, so it means that there is a chances that there will be a contamination due to this graphite. So graphite nothing but your carbon. Okay, so there is a chances that this molten state will molten silicon will also get contaminated due to the carbon. Fine, and these are the some byproducts that will be come out of this chamber. So I hope this discussion must be clear. So whatever I have discussed, okay, this picture I have taken from the SMZ book, okay, and now we can see whatever steps I have discussed, you can see in the next slide. Okay, this is the more detailed picture you can see there. I have already explained you this picture. I have actually this picture is there in the JD Plummer's book, but what I have seen is that picture is black and white. So I have taken this picture somewhere from the internet. Okay, so this is the actually system that you can means you can realize how it look like. Okay, so I already told you about all the fabrication steps. Okay, so these are the fabrication steps. You can see we are taking the pure polysilicon, okay, which is placed in a graphite crucible and heated up to its melting point, which is around 1412 degrees centigrade. Then we have to heating is done by the RF induction or thermal resistance method, whatever we can follow, but mostly we are following the RF induction. Then a crucible keeps rotating during the growth and to prevent the formation of the local hot or cold regions. As I told you that this rotation is actually being used for maintaining the uniform temperature throughout the crucible. Then a suitably oriented seed crystal. I told you about the seed crystal. Okay, this seed crystal is of silicon only. Okay, for example, crystal plane that we have taken as crystal orientation 111 is suspended over the crucible in a seed holder. Seed crystal inserted into the molten polysilicon. Okay, this seed crystal inserted into the molten polysilicon until it starts melting. So as I have already explained it, that it will start melting, and then as soon as it starts melting, we have to start cooling it up. Okay, so it is then slowly withdrawn and progressively freezing at solid liquid interface. Okay, and that will yield a large single crystal. Okay, and the typical pulling rate is about few millimeter per minute. This is what we have to maintain. And I told you that this pulling rate will be deciding you what will be the diameter of the single silicon crystal that will grow. You remember that if you keep the pulling rate very slow, if you do it very slowly, then there is a chances that the seed crystal will completely melt down in the melt. Okay, and you cannot grow the crystal. So that we have to take care. Okay, it should not be too slow. Otherwise, your reverse process can also happen, that the seed crystal will melt down and you will not be able to grow the single silicon crystal. These are the some pictures. I hope this is very much clear. Okay, so what we have to do is we have to first pull it down. This is the seed crystal that is connected at the bottom. Okay, and then when it will be pulled it down, it will start melting first. Then when we pulled it up, okay, this is our liquid phase, which is actually solid, starts solidifying. Okay, so when it will start solidifying, you can see when it starts solidifying, it will be this kind of solidification will take place, and you will get the this type of single silicon crystal, which is we called as the ingot. I hope it is very much clear from the picture. So what is the basic disadvantage, if we can say? The disadvantage of this methodology is, first of all, we look at why we are going for, why is Czochralski technique is very much popular. Okay, so the Czochralski technique is very much popular because its system is complex, but is still the way we are growing the crystal is simple. Okay, and the thing is that it can be able to, means it is able to grow the large diameter of single silicon crystal. This is one of the advantage. Okay, a large diameter of crystal can be grown. Okay, this is the advantage of having the Czochralski technique. And if we say about what is the disadvantage of this, the disadvantage is that because this polysilicon will be in the molten state, it will be in the liquid state, there is a chances that it will be get contaminated due to the oxygen present in the silica crucible, and there is a chances it will also be contaminated due to the carbon, presence of the carbon. Okay, so there are two types of impurities: oxygen and carbon may be incorporated in the crystal. This is the disadvantages. Okay, so sometimes we need a further purification even after that. Fine. So this is our Czochralski technique. Okay. Sometimes it is also called as the CZ crystals. Okay, CZ crystal. This ingot is also called as the CZ crystal. Okay, Czochralski crystals. Fine. So I have taken some of the pictures. Okay, this picture I have taken from the SMZ book. Okay, I have taken from the SMZ book. You will find it there. So this is one of the picture how it looks like when we completely draw a single silicon crystal. So after pulling it, it will get solidified and this type of cylinder will be formed. Okay, so this type of cylinder will be formed. And you can see the typically in this range, okay, we are manufacturing the ingot, which is having 8 to 16 inches of diameter. So from 8 to 16 inches of diameter, we are uh, drawing the single silicon crystal. Okay, and after that we need to cut them into a thin disc shape wafers. Okay, so typically when we cut them into a small or very thick very thin discs, this particular thickness we can choose. Generally we are choosing this much of thickness, like 0.50 to 0.75 thickness. Okay, it can be varied if we require, means according to our purpose we can change it. Okay, and then it will be polished and then it will be marked for the crystal orientation, which particular orientation we have taken for crystal growth. So basically we are using 111, but we can also choose the other crystal orientation like 100. Fine. So I will be discussing in detail about this. So what are this 111 and what are this 100? So that I will be discussing in the later lectures. Okay, so I hope this must be clear. So thank you for today. We'll be continuing from the next lecture. Thank you.